And again, welcome everyone. I'm glad to present this undergraduate research work actually, and I'm very proud of the group of students that you just mentioned the names: Sree, Benjamin Greenfield, Benjamin Placzek, and Stephen Atilho. They have been supervised by myself and by Professor Nassar too. Both of us are professors of computer science at the University of New Haven. The project is a nice capstone project, applied software engineering research project for undergraduate students, bachelor degree. And as you can see, the paper has won a couple of awards, got the chance and the privilege to be accepted for publication in this prestigious conference today. And of course, recently, actually, the group of undergraduate students who graduated this summer actually decided to take the adventure, or let's say the journey of a business experience, and they actually funded a small company in order to try to sell this solution to potential customers. And with no further delay, I'm going to tell you a little bit about this project. So the presentation today will follow this outline. We're going to talk a little bit about the context of the project, the problem formulation, of course, a couple of related work overviews and discussions. And we're going to talk a little bit from a software engineering perspective, the requirement analysis that has been followed, the software architecture, the methodology that has been applied, a few user interfaces, and a highlight of the results. Of course, a discussion of the work and some of its limitations and opportunities to address those limitations in future work. So the context basically is related to the parking problem. Parking is one of the biggest complaints of any college campus. Those students, when they started their capstone project, they looked at their campus and they quickly realized that the limitation of space in parking lots is actually deeply affecting their learning experience, from a stress, from costs and expenses, from convenience. All those factors have been addressed, and they tried actually through this project to contribute to improve or find a solution while using technology and new trends in order to offer a better experience for commuters, as our campus is half commuters' house and half of the students are actually hosted on campus or housed on campus. So as much as 3 times the amount of carbon dioxide is emitted while parking versus driving normally. So basically, when you are hovering or when you are cruising in a parking lot, trying to find a spot, and when the campus is wide or the organization is wide with multiple parking lots scattered around the space, finding a parking spot is a challenge. It increases, as I said, the stress. It might affect actually the productivity of the person, be it the staff, faculty, or students in this case, because we are applying, or let's say experimenting this project on a campus context. So the problem is creating new parking lots in order to create more parking spots or places is prohibitively expensive, especially in downtowns, like, for example, the New Haven campus, which is located in the downtown of the city, and real estate is very, very expensive. Upwards of 90 million new cars are made each year. You know that. I mean, we continue to produce more, we continue to consume more, which means in order for the parking capacity to scale up with the number of cars that are produced and put on the roads every year, it's basically a failed race. And reservation style solutions, where you are using those mobile apps or whatever system in order to reserve a specific lot, is quite complicated as a solution and does not scale well in context, in dynamic context, such as a campus where we have in and out visitors and cars in that specific space. So that made us think and consider what options, what solution can we create in order to improve or to better manage existing parking lots and existing parking capacity of organizations such as, for example, a campus or a university such as the University of New Haven. Examples of related works or solutions or technology that exists in order to manage parking lots include, of course, the reservation systems, the picture as you can see to the left, where you can actually reserve a specific spot for a specific time and you will be paying for that reservation. The logistics of occupying, or let's say allocating that spot or that space to a specific driver, and the management of that reservation is quite complicated. There is also the parking sensors, where the spot or the location of the car is detected in order to see if it's occupied and not occupied, and if it's occupied for how long and so on, in order to generate all that logistic and operational process in the back. And these are just a couple of examples of the many solution and technology that have been enumerated and analyzed in the paper. I invite you to have a look at that. So when it comes to the time to us to propose the solution that we wanted to create, we thought about it as we have parking lots and we have cameras, what we call CCTV, or closed captioning circuit television systems, which is basically a network of cameras. The technology is not new. It has been around for a couple of, for a few years, I would say. It's not, I mean, it's not sensor or Bluetooth or those advanced technologies. It is there. It has its limitation. I'm going to talk about it, but at least it is already installed, which means from a cost perspective, it's basically null to very limited extra investments in order to leverage that security layer of cameras in order to transform those images, instead of a tool to monitor or to provide human-based security, someone who is watching the screen and see if everything is okay, into a system that will process automatically those images and create a better experience for students, staff, and faculty, and any commuters or driver who is using the campus parking lots. So we planned to use those cameras. We wanted actually to analyze the images captured by these cameras in order to detect the numbers of available spots in multiple parking lots. It's worth to mention that the university has a 19 lots distributed across the campus. The average capacity of each lot is between 60 to 80 spots or cars. And we wanted actually to have a coverage that will give the user the capacity to analyze the 19 lots from a single portal. So that's the bullet number 2. The third one is to generate predictions. So basically, based on the data that we're going to be observing and extracting, collecting, and analyzing day after day, we would like to create a certain model in order for us to predict the occupancy or availability of lots, and hence help people manage and plan their activities when they are on campus. And finally, we wanted to provide a tool to suggest optimal parking lots based on time and decision, kind of a parking assistant system that will match the activity, the location, and the time of that activity on campus with the best lot for parking. Of course, that's derived from bullet number 3, which is the prediction that we generated in order to give a user some assistance. So now in the following slides, I'm going to talk a little bit about the live prediction lot availability, the intuitive, of course, user interface that we created, the mobile platform that we put together, the parking availability, and finally the parking assistant that I just shared a few hints about it. Again, our goal is to not use any extra technology or hardware in order to keep the costs limited, and leverage or reuse existing infrastructures, which are camera infrastructure, which here in the US are basically the standard, the minimum standard of security level for any parking lots. So basically that's actually where we start when we talk about parking lots. We expect that most of the parking lots or existing parking lots are already equipped with those type of equipment. I'm talking about the CCTV, of course. This is a short software architecture diagram representing the University of New Haven, for example. Several layers, the computer in order to have the database and the application backend hosted at the university levels. We're going to have the parking availability software and all the modules that are going to be supporting or implementing those requirements that we talked about early. And of course, you have the UI parts, which is the user mobile device. For those who are software developers out there, this is nothing but an adaptation of the model view controller pattern or architecture style for software development that is very popular, especially for mobile applications. The project's methodology followed an agile approach with bi-weekly sprints, and it's a capstone project, so it's a fall and spring semester. And as you can see, this is the burn down chart, the students when they started with the capacity or an overall volume of work for the project of 420 complexity units, if you accept this term. And as you can see how they worked their way up till to the end. And you can see sometimes they were a little bit behind in terms of objectives, slightly behind, and how the curve met finally the objectives by the Sprint 17s, which basically was the end of the month of May, the end of the spring semester, in order to basically produce that MVP, the minimum viable prototype of the full solution. The user interface, we opted for a native React user interface in order to ease the transformation of that web interface into a mobile application. And as I mentioned earlier, we have different parking lots. In order to run the project, we used 3 live parking lots for prototyping, and then we scaled it up to the 19th. And these are just live and actual screenshots from these lots. And as you can see, the first one, for example, 8 spots out of 14 were available, 9 out of 23 for the admissions lot. And for Hoffman Street lots, there were 189 spots available out of the capacity of that large lot, which is 197 spots. Now, talking about the detection methodology, as we mentioned, we are using cameras. Some of the lots have single camera, some of the lots had multiple cameras. Of course, the single camera is constraining because we have a single angle of view, and that in terms of detection and creating that convex hull and the boundaries in order to detect these objects and to recognize them, classify them as vehicles was limited. If we had multiple streams or multiple feeds from different cameras, the process was, the accuracy and the quality of the process was actually better. And as you can see from the collection of images from cameras to the image processing in order to detect those objects. And then from there, we are actually feeding a database that is feeding the user interface in order to have a live real-time availability of each lot, so that the user, when it comes to campus, can check that user interface and determines live now how many available spots are in which lot. So that being said, now the problem is, if we are talking about immediate parking, the view of the actual situation or the current situation is enough to address our needs to park our car. The problem now with the parking is when you are planning for future activities, and imagine yourself a student who is planning for his courses or her courses throughout the week, and we would like to have a class in this building, and the building is basically in proximity of a certain parking lots, and then you have another class in a different building in the afternoon, and it has different parking lots. How can you manage? How can you predict which parking lots you should be parking in or targeting for parking with respect to your activities if you don't know what the trends of availability or occupancy are? And that's where the analytical predictions comes into play with respect to the time series, of course, data that we collect. We were able actually to have trends, and those trends take into consideration, of course, weather conditions throughout the year, events that happen on campus, classes, frequencies, or let's say visits, frequency of visits of drivers from outside the campus to the parking lots and so on. As you can see, the pictures here to the bottom, that's the availability prediction model for the Hoffman Street parking lots. Finally, the smart feature that we wanted our parking lot to have is actually, as I mentioned earlier, the parking assistance. Let's say you have your calendar, and on your calendar you have a set of activities. Could be a meeting for a staff, or could be a class for a teacher that is teaching a class in a specific classroom building on a regular basis, for example, like a few days a week or a couple of days a week and so on. Or a student who is taking several classes every day in different buildings and different classrooms. What would be the best, again, that's the optimization part, the best location to park his or her car in order for you to be on time, to have a reasonable travel time between the parking lot and the buildings. We are in the United States, we are the Northeast, although we enjoy the summer and we love the 4 seasons, but sometimes winter is a rush here and very harsh, and the snow, cold temperature, winds, weather conditions might be important to consider when you are parking your car, so that you don't have those long trips or walking travel or walking distance between the parking and the building where your target is. So we try to create this spatial temporal analysis tool where you can specify the activity starting time, the activity frequency in terms of days of the week, the location, which building out of the buildings of the entire campus, and your type of commuters, which is very important because although we have 19 parking lots, we have different parking permits, and some parking lots are reserved to students, some parking lots are basically open to public, some are restricted to only occupants from the university. So the parking permit type is also important in order to see your accessibility to those resources. And with respect to those activities that you're gonna mention here, with respect to the prediction model that I was talking about early, we were able actually to build this parking assistant, which basically does nothing but run the analysis parking lot by parking lots in order to verify the prediction and the occupancy for those times and days, and then suggest with respect to the preferences of the user and the starting time of the activity, the travel time, in order to recommend the best parking lots and the estimated arrival time for that specific activity. The second part of the image processing, of course, I'm pretty sure many of you have expected that. As we have the pictures, we can actually do extraction of or character recognition and extraction for the license plates. That is useful not only from a security perspective in order to monitor the parking lots and make sure that those who are in the parking lots are basically respecting the parking permit type, time, and accessibility, but also from a security perspective. As you know, in the United States, as well as many other locations, security is important, and any activities, suspicious activities related to criminal activities or terrorism are always in our minds, and any efforts to fight those activities is also welcome. And that's why we were able actually to use existing algorithms, machine learning algorithm actually, that extract and recognize characters in order to build those license plates. We were able to create databases that basically track those license plates when they just parked, when they left the parking lots, where in the parking lot they have been parking, so that we have a clear information. If anything happens on campus, we can run those type of analysis and extract the data and provide public safety with the information that they actually expected. If we go to the discussion here, the project was not a smooth journey. It was actually quite a challenging and exciting project with some technical constraints. We have, as I mentioned, 19 parking lots. We realized when we were integrating and scaling up that the cameras that we were using actually are not in the same generation, all of them. Some of them were equipped with FTP connection or connectivity. Some of them have or were equipped with other connectivity technologies. So having those cameras to all communicate with the server platform that we put together in order to collect the images was quite a challenge. The camera coverage was also a challenge because, again, those cameras belong to different generations with different technologies. Some of them were actually kind of distorted image view, which made the extraction of and classification of objects quite challenging. And automating that license plate reading and character extraction was also challenging because, as you probably know, Connecticut is a small state, and we have students and faculty and staff who are working and attending the University of New Haven, but coming from different states. So just focusing on the license plates from the state of Connecticut was actually not enough. And we had actually to expand in order to include the neighboring states who are actually commuting to our campus, including Vermont, Rhode Island, New Jersey, New York, Massachusetts, Maine, I mean, you name it. We have like a quite large pool of license plates, which actually initiated the project in order to recognize all the license plates of the 50 states and territories here in the United States to make our system exportable, as I mentioned earlier. The future work, what we are working on now is actually to move that web interface, native React web interface that we created into a mobile application. We would like also to extract, or let's say leverage, that license plate security or extraction and recognition in order to feed more security so that we can, for example, follow or track the behavior or the positions time of a specific license plate over the past day, week, months. I mean, it's just about digging in that database that we created. And also we would like to be able to issue ticketing, automated ticketing that is sent automatically to the user so that we can save on the costs of active or live agents who are actually securing the parking lots on using their vehicles in order to go and issue tickets for those who are violating parking rules. We would like to automate that and make it fully digital, especially that we have the camera, we have the type of the permit, we have the license plate. Nothing prevents us from checking and making sure that that car is violating or not the parking rules. And finally, hit and run here in the US is a national sport, especially when people are leaving in a rush or in weather conditions and so on. So you're never protected from someone who would probably hit your car and hit your mirror or your bumper, and you come to your car and you find the damage, and you can't help but wonder what happened. We would like to exploit and use those events and those situations, especially that we have access through the camera to everything that is happening on campus, in order to say, okay, this is a situation involving a vehicle collision, and inform both parties in order to say, this is what happened. public safety on one end, the owner of each vehicle, so that no hit and run that is not analyzed or followed up happen on our campus. And hopefully by making that application available for other campuses and other organizations that opt or are willing to manage their parking lots in an optimal manner or an intelligent manner will benefit from that solution. That's pretty much my story for you today about Smart Park. Again, I cannot tell you how much I am actually proud of my bachelor degree students in computer science and software engineering for what they did. I wish them all the best for their business journey now with this startup. And I'm looking forward to see their project, their business, and their application and customers successful in the future. And thank you very much for your attention.